Okay, before going on to orthogonal trajectories, I'm going to revisit example number 2, in which we considered the case when the vector field v was equal to x squared minus y squared 2xy. I'm just going to focus on the first quadrant, and we need to note that x squared minus y squared could be positive or negative in that first quadrant. So when x squared minus y squared equals 0, we get y equals plus or minus x. So that y equals x will be that, and y equals minus x will be that. So this is y equal to x. This is y equal to minus x. So that when we consider the signatures of the vector fields or the directions in each of the quadrants, each quadrant will have to be further split into two parts. And that is why we needed to indicate this as section 1 and that as section 2. In section 1, for example, x and y are both positive, but x is greater than y, so that x squared minus y squared is positive. And that implies that in this section, vector field v has the signature positive, and 2xy of course is positive. In section 2, however, x is less than y, even though x and y are both positive, but x squared minus y squared is less than 0, so the vector field v takes on the signature negative, positive. Thus, the direction of the vector field in section 1 in the first quadrant is up like so, whereas in the first quadrant, section 2, the vector fields point that way. Thus, when we go back to the sketching of the directions, that will be in those directions, whereas in section 2, it will be in that direction. And of course, we showed that along the line y equal to x, so along y equal to x, the vector field v had the signature 0, positive, and those directions were straight up like that, so that when we go back to the first quadrant, this means we have vector fields that are positive upwards. And when we join the directions of the vectors in that first quadrant, we get that, that, and that, which when you put together reconstructs like so. So that was just recalling and sorting out what happens to the example in number 2, and we do this for each of the quadrants 2, 3, and 4. Each of the quadrants split into 2 further parts, and one needs to analyze this separately. And then of course we went on to the example 3, which dealt with a 3-dimensional vector field, and of course there we could not get into drawing the profiles as we've done here, but we had to analytically solve dx dt equal v1, dy dt equal v2, and dz dt equal v3, etc., etc. You may go back to example number 3 to sort it out. What we do now is look at the notion of orthogonal vector fields. Orthogonal vector fields are those vector fields to the given vector field v that are perpendicular. Orthogonal means perpendicular. So in this section, we consider orthogonal vector fields. So doing this by way of example, in the first place, if your vector field V has coordinates v1, v2, and this is discussed only in the two-dimensional case, then the vector that is perpendicular to this vector would be of the form v2, v1, because the vector v dot the vector minus v2, v1 is equal to 0. So to consider perpendicular, the orthogonal vector fields, we'll need to consider that vector field. So in this case, to find the shape of the vector fields that are orthogonal, we will now solve dy dt over dx dt, which by the chain rule is dy dx equals v1 over minus v2, which is equal to negative v1 over v2. You may recall that to find the vector fields, at least the trajectories, we needed to solve dy dx equals v2 over v1. So for the orthogonal trajectories, we solve for y in terms of x, or we solve for the function that is a solution to the equation given by this. And this is for orthogonal trajectories. Right, so example. We go back to the previous example with vector field v equal to x squared minus y squared, once again 2xy. Then the orthogonal trajectories are given by solving dy dx equals minus, we know what v1 is. V1 is x squared minus y squared over v2, which is 2xy. And then we go about in the usual way solving this first order homogeneous differential equation, which again, recall, we do by letting y equal to vx, replacing dy dx as we did in first year. That will be v plus x dv dx. You solve for v in terms of x, replace v by y over x, and you get a set or a family of circles. This time the circles are those whose center are on the x-axis, passing through the origin as in the previous case, as in the case of the trajectories. So without getting into the method for solving, what we end up with are circles. The orthogonal trajectories are circles having the following profiles. So they are centered along the x-axis, passing through the origin, and similarly on the negative side. There are a family of circles doing that. You may recall the trajectories in example 2 were those whose centers were on the y-axis passing through the origin. So these are the orthogonal trajectories, orthogonal to the trajectories we sorted out in the first case. So that brings us to the end of trajectories, and in essence it gives us the end of the chapter 2.